We got rid of that broadband monster, which is fascinating. The Bolton, I'll load it on the GitHub site for this these lectures. But look at what happens here when we toss the globe 9 times, get 6 water and 3 land. We start with a prior. We already went through this process where get a prior, it's pretty much agnostic. We add some water, we get that straight line, then we add another observation, it's land, and we get that quadratic. And then we do it a third time and we get water. And notice what's beginning to happen. We're getting more shape as we add more observations. We get more shape. We also get a narrower, more precise idea of the range of possible proportions of successes. And we also begin to see, just with 9 throws, imagine doing 1,000, that it begins to pinch in. If I can pull this up here. Begins to pinch in right here and right here. That's called an inflection point. It's the same inflection point that we saw with the Galton. That's Galton. Regaling everybody with his not a parlor trick. It's something that is going to happen every time in our Sandy Gelman at Columbia and Cosmos Shalizi at CMU have written about the hypothetical objective deduction process. We're actually doing deductions here. And we're creating new knowledge with that because we're building a structure with some very, very simple deductions to get to this point. Look at how that pinches in. An inflection point. Now, there is some math that will allow us to go from a binomial model, and we can make a Poisson model out of that. That's in the book that's associated with these lectures. Yes, we can do that. We can also take that same binomial model and make it into another model, which is what Gauss found out. And the beauty of this is we take a 1 parameter, we're solving for a proportion of successes in the binomial, and the intensity lambda with a Poisson. It turns out that that's all you need to know in order to establish the mean and the standard deviation of either the binomial or the Poisson. We're going to look at that in the next lecture much more directly. But Gauss began to see this and began to notice this pinching in, and being the mathematician he was able to derive a very, very specific functional form to describe this pinching in, this process that if I take this down to 1,000 rows of the globe from lecture number 1, that we will end up with a functional form that looks, well, we're back to E again. That looks like this. And that is also called a diffusion or dispersion operator. It describes a lot of different things, everything from option prices and finance back into the way particles interact in a fluid, going way back to distribution of temperatures in a piece of metal. And then ultimately, it will be used by us to detect and solve for a most plausible mean GPA, as well as a most plausible, at the same time, both and, a most plausible environment in which our data seem to be inhabiting. So that's critical. That piece is critical, right? That we're actually going to be solving for this. Now, he adds a sigma here, and Z is something called, and here's our GPAs. We center the GPAs, each and every GPA around its mean. Those are called deviations. They're also called errors. And Gauss invented the error function. And then we scale it and say deviations of GPA around the mean per unit of uncertainty that we're going to measure with something called the standard deviation. And we're always asked, I'm not the only one always asked this, what's standard about standard deviation? We'll leave that for another time, probably, plausibly. Okay. So this is going to be our observational model, which is born out of an intuition that the more times we subject our model to more data, and that's the notion of continuous movement, where we have one toss, two tosses, and we now do three tosses and four tosses. What's between the one and the two tosses? Well, nothing, just one and two tosses. But we can say what's between 2.67 and 3.125. We can find numbers in between there. And that's the notion of continuous numbers. So let's take some of these intuitions. Let's build them. We have a sample of data, and I've included a small guide to doing some computations. We have three pieces of data. That's under the G column here, 3.5, 2.5, and 2.0, three different performance periods. We can add these numbers up and get 8 and divide by 3 to get an average of 2.65. The formula for mu in this, if we were to, let's calculate mu off of the data without any notion of how plausible this number is, and it might not be very plausible, by the way, is equal to the sum from I equals 1 to n. Each of these G values, we have 3 of them, and then we divide by that. This would be equal to 5 plus 2.5 plus 2 divided by 3. 8 divided by 3 gives us 2.67. And we're going to call that a measure of central location. Now we can take deviations from that and see how far away. Here's our 2.67 location of our data. And we have one data point that's down here at 2. Now we don't need anything quite that thick, do we? Okay. There we go, 2. Another one at 2.5. Yet another one at 3.5. Really good performance period there. And we can look at deviations. That's already good. The 3.5 deviation is 0.83. Notice it's a plus 0.83. But the 2.5 is below the 2.7. 2.7 is like a benchmark. by grade point number of minus 0.17. And the 2.0 is well underwater there. 2/3 of a grade point underneath. And we can get a little better feel for the data here with this variational analysis. The problem with it is if you add it up, it always adds up to 0 every single time. You can prove this yourself over and over again. So the average of the deviations themselves is 0, but that's useless to us to get an idea of how deviant those are from, or how much error there is between the mean and each one of these observations. We have two fixes for that. We can either take that deviation and square it and make these all positive numbers. Sum those up, 117, 1.17. Divide by 3. Actually, we're going to divide by 3 minus 1, or 2. And then take the square root of that, because these are deviation squared, or grade point average squared, which is a meaningless number to us. I don't talk to anybody about square. I talk to people about square footage in an apartment, but not about square GPA. It doesn't mean anything here. We're interested in the level of GPA and how dispersed it is. That's the answer we're going to get from this kind of a simplified analysis. And when we do all of those things, we get 0.76. That's the average level of dispersion. And that formula is pretty straightforward, just like the mu. Sum from I equals 1. Each of the deviations from the mean squared. This time we take n minus 1. All sorts of interesting reasons that we'll go into a future date. It's like we have 3 observations. It's like losing one of them in the averaging process. Why? Good question. One of the observations is in this mu calculation right here. We have each of the observations actually in there already, so it's like losing one now. And it's like it acts as if there are only 2 observations of this. So we perform this, we get positive numbers, and this gives us a measure of dispersion that is in the units, because we're taking the square root of it, in the units of GPA now. The other fix is to do the absolute value of the deviations. It gives us a similar number. We take its average of 3. I think to make this reasonable, you'd have to take it by 2, but most people take it by 3 in the formulas out there. I'm not going to get into that contest ever. And we get a smaller level of dispersion with the absolute deviation, which is usually the preferred one with small amounts of data like this, or widely disparate data like this. And there's another one that we can form, which is called the Z, or the Z score, which takes the deviations, the 0.83 in this particular case, that first deviation, and divides it by the standard deviation of 0.76. So you take a deviation, positive or negative, and divide it, ask how much of that deviation is there per unit of standard deviation. And the Z reports how many standard deviations you are away from the mean. And of course, you can be in either direction. One whole standard deviation from the mean is the first one, 3.5. One whole standard deviation. Remember, the standard deviation is 0.76. So 3.5 as a GPA 1, is equal to the mean of 2.66. plus 1.09 standard deviations times the standard deviation of 0.7. So we can retrieve it that way. It's different ways of talking about the same thing over and over again. And it's a way of communicating results when some things are easier for models to understand, some things are easier for people who have to consume the results of the models to understand. What's real interesting here is because it's the deviations in the numerator, they'll always sum up to 0. But what's even more interesting than that is the standard deviation is always 1. Always 1. So we burn this into our memories so we don't have to remember what the means or is means or any other language here. The mu of a z-scored, a centered, scaled per standard deviation, 0, 1, 1.0. Now, Gauss and others didn't always look at it this way, but that's the standardization that we seek here. And creating a z is called a standardization. Some people would call it a normalization. I would avoid that language. I would avoid it, run in the other direction. It's a standardization. Standardizing according to standard deviation. So, well, that was fun. We have some statistics here. We have a range here, by the way, from a minimum of 2 to a maximum of 3.5. And when we go back and look at our hypotheses, see, we didn't do too bad a job here. We go from 2 to 4.0. So 2 is the minimum. We might have taken 1.5 for that. So we have our form. Our form, quite literally our form. It's otherwise all of this is just the shape of water, which is pretty fluid. You can make it any form you want. But we've taken our ideas and given them some form. Yes, yeah, formulated. And we now have something else. We have a environment for sigma that's going to be 0.5 or 1. The data says all by itself, without any interpretation whatsoever, that these 3 numbers have a standard deviation of 0.76, but a mean absolute deviation of 0.5. There is a low number, and there is a high level of uncertainty or dispersion in the data. That's what that sigma is going to tell us. We've got our sample, and we're going to use this new counting rule that we have. Which will hopefully help us out a little bit here. I'm gonna try that rule down here with the calculation for a particular, here it is. Let's see if we can see all this together. For a particular hypothesis, let's choose hypothesis number 8. Hypothesis number 8, and let's also choose one piece of data, the first one, 3.5. Let's do the calculation, at least to say that we have done the calculation. Exactly by hand. You can get your slide rules out, yes. But this probability is going to be equal to 1 over sigma square root of 2 pi. By the way, whenever you see pi in a formula, probably has something to do with circles. And that is indeed the case with these formulas. Epicycles minus 1/2 z squared. Each c is a GPA minus its mean, deviation of the mean, scaled and squared. That squared really makes things interesting from, it's what's creating that pinch in. That square is, that negative and the square are creating this lovely shape. It's very much like an S. When we do this calculation, you see that 1 over sigma square root of 2 pi, well, I've chosen the right sigma, it's 1. 2 times 3.14. That's a repeating, not a repeating number. We won't talk about whether it's rational or not today. E is a minus 1/2. G is 3.5 as it deviates from a mean, hypothesized mean, by the way, of 3, scaled by an hypothesized sigma, not the one in the data. It's the one in our hypotheses. And if you do your calculations correctly, 3989 times 0.8825. And if you do all of that correctly, to 2 digits, it just goes to 0.35. That's what we should be getting here, a little over 35%. And that's indeed also what Excel will report, where it uses a function to calculate all of this. We'll look at that in another part of this lecture. Okay. So we still have to multiply this 35 times the 0.1 times whatever it is for 2.5. I think it's also 0.35. And whatever it is for 2. Multiply them all together. And I have done that here. And here it is. Let's see if we can blow this up. There we go. It's the same story over and over again. Here's number 8. That's for that piece of data, that piece of data, and that piece of data. Each of these probabilities multiplied together, because they are both and statements, we see the probability of observing 3.5 and 2.5 and 2 and this hypothesis. 4 things we see together, both and statements. The chain of both and statements, we multiply them together, get this kind of small number, 0030. We do this for each of, again, we have 2 hypotheses here. 2 sets of hypotheses. And altogether, we have 2 different sigma regimes and 5 different levels of performance, mu's, each occurring with 10% probability. And we multiply them all together, sum them up, just like we have done all through all of the other models. We have 10 different hypotheses and different probabilities of an hypothesis and data. I use these data here. All these these are all joint probabilities. And now we are normalizing them. Normalization here, orthonormalization, is putting numbers between 0 and 1. And from a practical analytical point of view, we're looking at the contribution of each of these hypotheses to a whole mix, 10 of them. We come up with 2 sets of hypotheses, and one for each regime. There's the low, there's the high sigma. And Each one of these will add up to whatever. I mean, we have to add all of these up to get 1. All of them up, because they all matter. They're all joint and jointly together. And we see that the range of probabilities for the low volatility environment goes from a 0.02 up to 0. And we see that the range of probabilities goes from 0.1 to 0.01 for the high volatility environment. In other words, they're less concentrated. They're a little bit more spread out in some ways. Okay. Now, the next step of this process is to put this list side by side with this list to get a better idea of what they could be telling us. And that's over here. So here's the low volatility environment. Here's the high volatility environment. And we put them side by side. They're interesting comparisons. 20, 17, 24, and 15. Now this is the low volatility environment is going to be a little bit more compressed than the higher one, and that makes sense. It makes sense in this way. They're both going to work around that 2.5. Yeah. Here's the low one. And here's the high one. Going to have different volatility profiles by the dispersion. By what's in the tail or not. We don't have much in the tail here at all. Here we have a little bit of stuff going on. That's the higher plausibility. This is much more going on in the tail. Much more, 2 is much more plausible in the high volatility environment than in the low environment. A 4 is also in the cards. Should you want to go into that level of high performance in the high volatility environment? Now, it turns out that we can figure out the probability of a mu of a level of performance now. It's not 2477, it's not 2019, it's both of them together because these are mutually exclusive, completely exhaustive potential experiences with GPA. In the low volatility environment, you can get 2477. You can either get that or you can get a different environment, mutually exclusive, and we're only considering these 2 environments. Get a different plausibility level. Altogether, we add these together. Do check this math out. Almost 45% plausibility. It's much more plausible. But so is a 2. And now so is a 4. Really low and a really high. But notice it's moving in the lower direction. A performance counselor, a mentor, might say, let's see how we can move this from here up to here and propose a set of policies, plans, actions, who, what, when, where, how, why, changing habits, whatever it is, to increase the level of quote unquote performance. And that is how we might use this. And we would have guides for if things are very iffy, high ones, or not so iffy, the low one. How do we make things more certain for ourselves? Okay. And just move these sticks around. So we've used everything in our toolkit. We've used mutually exclusive. Oh, by the way, we can also ask the question, what is the probability of a low environment? It's 42%. And what's the probability of a high environment with this data? 57%. This data is shocky. Okay, it's got noise in it. And Gauss would say, yeah, it's error ridden. It is. It's only 3 points, remember. But the high volatility environment is more plausible than the low. How do we know? More plausible. And again, we're adding that, plus that, plus that, plus that, plus that, because these two are messy. Completely exclusive, completely exhaustive experiments, if you will. Well, we have all of that done, and I think we're going to, let's see if I can get this back to where it was before. Look what we've done. We posed a question. We have formulated reasonably sounding hypotheses. We sampled some data and look at some of the statistical properties of that data. Not inferential, purely statistical. Come up with an interesting counting model that takes into account something we have seen before, that with increased numbers of rows of that globe, we get a pinching in. It's less likely to have big deviations. That's the idea there. And I haven't gone too much into that. I'm going to get a little bit more into that as we look at the way the data interacts with the hypotheses with a slightly expanded model, a very similar model to this, but using Excel. And I think it'll be able to show us a little bit more easily how that pinching in. When this distribution pinches in, this Gaussian distribution pinches in, it means there's less probability in the tails, which means that very high and very low tail levels, very high GPA, very low GPA, are not likely, are not plausible. Now, if you can live with that, that's okay. A lot of people don't live with that and try to change that idea and again move that mean up and make it more certain. Okay, that's what they're going to probably try to do. People who trade don't do that, by the way, but that's a different mark. That's market reasoning versus performance reasoning. Okay, we might have to separate those two. And we formed a couple of inferences. We actually calculated the most plausible mean and also the most plausible one that is most compatible or consistent, most plausible environment, high volatility or low volatility. Interesting idea there. And I think we will leave it at that. That's quite a bit to digest in one sitting. Play with the numbers, play with the formulas, use a calculator, go back and refer to whatever math you've had to high school where means and standard deviations were involved. This is a very light review of that. But we come up with a new counting model, which is very consistent with the Poisson and the binomial because they all are related to one another. And we will find that out in another lecture, exactly what that means. I'm going to leave you with this. Thank you again very, very much for your kind attention, especially with some of the technical difficulties of moving this thing around. Figured that out midstream. And I leave you with Lecture 5, Part 1. Take care and enjoy.